Okay. One change is that exam 2 got moved up. Let's see, well, and that changed a couple of these lectures in here, but the main change is that exam 2 is on July 24th. That's mainly to get it in before the drop date. It was the week after the drop date, so I moved it up to where it's before. I guess that's the Wednesday before the drop day on that Friday. So now you'll have 2 exams before the drop day. Web work should be going, so you should have actually 2 sets now that they're all open. You can actually work on any of them that you want to, but now homework 1 will close on Wednesday of next week. I believe homework 2 will close on that Thursday, so don't get behind on them just because they, one of them isn't that big a deal, but you'll eventually have more or less 3 going at once in different stages, so don't get behind on them. You can email from within WebWork. There's an email instructor link when you're logged into WebWork, and it'll send me your problem with your numbers and all the information that you've done. So that's the easiest way to get help, other than like asking questions during class or whatever. But that's the easiest way, most direct way outside of class to get help with that kind of stuff. Yesterday, we talked about force vectors. We talked about 2D concurrent force systems, static equilibrium in those force systems, and resultants, stuff like that. Stuff that you all should have done in 122 at some level. Today's stuff is stuff you didn't do in 122, but it's just the 3rd dimension tacked on to what we already did. So it's not a huge leap forward, and it's still in just the statics. So this is still pretty much just statics, no mechanics yet. So we're going to do these 3D concurrent forces. And one of the parts of that, well, not of 3D concurrent force systems, but in general to this class, is being able to draw free body diagrams. So we'll actually talk about that first. It won't come into play as much on these concurrent force systems. They're pretty straightforward on drawing the free body diagram, but we're going to go ahead and identify some steps. I have eight steps for creating this free body diagram for whatever it is that you're going to do some calculations on later. So the first step is you just have to identify the body of interest. And this could be a whole bunch of things. It could be part of one object. It's just whatever you're interested in solving, some kind of, normally you're trying to solve some kind of stresses or strains in this body. And so you got to identify the thing. But it could be part of this table here. It could be this whole room. It could be a rope, all different things. So you have to kind of identify what it is you're interested in. And then if you've got a picture of this, so I'm assuming that you've got some figure drawn or whatever, not a free body diagram, but a picture, or maybe you've envisioned the thing in the real world, I don't know. But if assuming you have a picture of the thing, then just draw a circle around this body. And what this will do is at some point, unless this body is floating in outer space, and in which case it already is a free body, then drawing a circle around it will force you to draw through whatever it's connected to. And once you've isolated this thing, then draw some kind of figure. And you don't have to be super artistic with this thing, but something that represents the body in its isolated form. So it is floating out in space. Oops, not the body. So you've got some figure. It's just a line drawing. Maybe it's a circle or a box, or maybe you got fancy and drew something that actually kind of looks like the thing. That part doesn't really matter, other than the fact that you're going to have to apply forces to it. So any relevant features where a force is applied, the point of application for one of these force vectors, you probably need something that represents that. Right now, with the concurrent forces, everything kind of collapses down to a point somewhere, that intersection point of all the lines of action. So for these free body diagrams, it can just be a little dot. When you get into non-concurrent force systems, then it probably needs to kind of represent the thing, whatever the thing is. But it doesn't have to be artistic. It just needs to be some little box that represents it. But right now it's floating on your page. You've drawn this figure, and now you need to draw a coordinate system for it. So right now we're doing, or yesterday we did X and Y 2D. So you put an X axis and 90 degrees from that, put a Y axis. Today we're going to do 3D, so we'll also put a Z axis in there. You just need a reference point to measure things from and create angles and dimensions and that sort of thing. So you need a coordinate system to reference. So now you've got a figure that's in a coordinate system. So now what you can do is when you drew that circle around the body of interest, you drew through some lines. And so these lines were other ropes or cables, or maybe they're bolts or pins, or maybe it's the other half of the body or whatever. You cut through something when you drew this circle. You've got to replace every one of those cut connections. We'll call them connections because they could be a lot of different things. So replace every cut connection with something. So a corresponding force, most of them are going to be forces. Some of them we'll put force vector for now. And it could be two. Maybe has to be two forces that represent what was going on there. Right now we're just doing with one, but there could be some scenarios where you have to replace this connection with two forces. Or a torque. We're definitely not doing torques yet. And remember, a lot of these torques we're going to refer to them as moments, but they're doing the same thing. Right now we're going to do replace all these connections with a force vector. So right now it kind of, most of the 2D concurrent thing, it's a strut or a rope or a cable, and when you draw the circle through it, there's just the one line in the cable, one force vector in the cable, and that's, you would draw some kind of arrow that represents that connection. So now that we've got that out here, now we've got a picture, a coordinate system, and some arrows drawn on it. But don't forget, look for other forces. So things like, in particular, body weight. So sometimes the weight of whatever it is that you're isolated, it actually matters. There are other things that could matter. Maybe there's a wind load. You got a sign on the side of the road, or the face of a building. You know, there might be a wind load on that. In our class, I don't think we're ever going to deal with a wind load of any kind, but don't be negligent about thinking about them. Maybe there's some kind of magnetic, you know, it's got a electromagnetic or a magnetic force that you have to deal with that's actually trying to move the thing around. Again, in this class, probably not going to happen, but body weight for sure is something that you have to make a decision on. A lot of times you can make the decision that the body weight is negligible compared to all the other forces that you're dealing with, but you do have to acknowledge that a lot of times body weight might be important on this free body diagram. And so in that case, draw an arrow, usually going straight down, depends on what you've got drawn there, but normally that's where it's going. 7. So you've identified all these, so draw these forces on that body if it's not obvious that you haven't already done that. And these forces are torques and are torques on the body, the little figure that you drew. Then finally, draw in dimensions that are relevant and angles. You know, how far is this cable angled from the x-axis or whatever. And then now you've got a pretty complete free body diagram. It's got the isolated body, It's not connected to any other things in the universe. That's the free part of the free body. And anything it was connected to before you cut it out has been replaced with an equivalent force. So if this traffic light is our thing that we're interested in, we would do something like, let's move this thing out of the way, or move that down. We would maybe go in and make it a little bigger. First step was identify the body of interest. So if this is our thing that we're interested in, maybe what we're most interested in is this little point up here. So we draw a circle around it. You know, that's one thing, that little connection point where these cables, this is probably one continuous cable. We'll treat it like two separate cables since it looks like maybe it's clamped right there. Or maybe you want to say, well, no, that's not the body of interest. It's, it's this thing. It doesn't particularly matter. It depends on what you're trying to solve for. Just in this particular one, let's draw it like this. We've got that weird little loop, that little loop right there, that thing. I'm going to assume that is not really exerting any force at all. That's the actual power going into this thing, and they don't want a lot of strain on the power cable. So I'm going to ignore that guy and pretend it's not even there. That's another thing that you have to do when you're dealing with these free body diagrams and just engineering mechanics type problems in general, is decide what's important and not. Let's draw it in a different color because it all is the same color here. So here's my circle. I'm going to draw it like that. Doesn't have to be a circle. It can be any shape, a closed loop. We can replace circle with closed loop so that it doesn't have to be a circle. In fact, we'll do that. So circle can be closed loop. Doesn't have to be an actual circle. All right, so step 2 was we want to draw some figure to represent what we've got here. So maybe we could, since this is a concurrent force system, we could go in and draw a little dot. Again, let's do some other color. Do that blue again. We could draw a dot that represents the thing. We could try to go in and draw this little shape right here if we wanted to. Whatever we want to do, we could draw the shape with some of this cable. We didn't actually cut the cable until over there, and we've got this, whatever that little block is. You can get as accurate or as abstract as the problem needs you to be. In this case, let's just draw something that kind of looks like this little T thing in the middle. One thing that I didn't actually write over here, but is a good idea, is draw big. So don't try to save space and make your little diagram tiny, because then at the end you're gonna have to put all this detail on it, and it's not like, unless you actually are working on a tablet like this where you can zoom in and make it bigger or whatever, then you're stuck on a sheet of paper and it's always that size and you can't get more information on it. And there's no reason particularly to draw this tiny little diagram. Draw one, if you're writing this on paper and you're starting out to solve a problem, the first top third of your paper, might as well devote that to the problem setup, this picture, what all kind of information are you, the given section, the top third of your paper. Go ahead and do that, or the top half if you want to be really big. But you're not gonna be sorry later on that you drew a big picture. You may be sorry that you drew a tiny picture. So unless you're very limited on the amount of paper you have, and then I guess maybe you have an issue. But I would say draw big. All right, so I'm going to draw something that represents this guy. Let's make us some more room. We don't need this stuff yet. So let's move that down. So it kind of looks like, I don't know, kind of like a little T. So there's the little body of interest. We can do whatever we want to with it. It had some cables coming off of it, so you could actually go in there and draw something that looks like a cable. Again, it doesn't have to be super accurate. Whoa, it might be more accurate than that, but I don't know what's going on there. And then there's something at the bottom there where it's connected to the traffic light itself. We'll kind of ignore that. All right. Next step, coordinate system. So since we think this is going to be a 2D concurrent force system with all those lines of actions kind of meeting right there, then it makes sense to me to make that the origin of a X and Y coordinate system. So that makes sense. Replace all the cut things with some kind of force or torque. Now in here, we're not dealing with torques yet or moments yet, so just forces. So I cut through right here, and so I have to replace that cut connection with some kind of force. That's a cable, and it looks like that cable would just have a tensile force in it. Tension is going to be an arrow that points away from the body, and it kind of looks like, now that I'm looking at my picture, maybe this one's supposed to be a lot more horizontal now that I look at that thing. So let's make it way flatter. And I cut through that one too. I cut through it right over here. So let's do the same thing. Put a little arrow there. And then I cut all of this stuff off. And that one, I'm just going to say, is the weight of the traffic light. And so I want to make it an arrow going straight down. Normally in your coordinate systems, this is force in cable B, this will be force in cable A. That'll be the weight of the traffic light. That looks like enough information for what I would want on this little picture. Look for other forces. We did body weight, W. Well, there probably is a wind load. We're not going to worry about it. We drew the forces on the body already. Dimensions and angles. There's no dimensions that are really necessary for this, but there are some angles. We can go get our little ruler and try to measure these things, assuming that this is lined up anyway. So that one looked like it was 3 degrees or so. So we can put a little 3-degree guy right here. And this one looks like it's 18 degrees. So we'll put 18 degrees here. I don't know how much a traffic light weighs, so we can either just guess, or we could go and try to figure it out. Let's see if there's any info out there on how much a traffic light weighs. There we go. 15 and 30 pounds. So let's be the most conservative. And again, this is a composite plastic one. This isn't an old school like metal one or anything. So looks like modern traffic lights at the most weigh 30 pounds or so. So let's be conservative and go with the 30-pound number here. So we'll put 30 pounds. Now we have something that's a free body diagram of our little T-clamp thing in the middle there. It's got the most relevant forces on it. It's got some dimensions, in this case just angles from horizontal. And we've got some variable names. I guess I should have specified that when you are doing this step right here, withdraw these forces or torques on the body, you should and label them. So either you know their value, the weight is 30 pounds, or you give them a variable name, FA or FB, the force in cable A, the force in cable B, whatever like that. Otherwise, they're just arrows. You need to turn them into force vectors that have magnitude, even if the magnitude is unknown. Now we could solve it. In fact, I didn't solve this one, but let's solve it since it's a reminder of what we did the other day. We assume this is in static equilibrium. That gives us 2 equations to work with. Summation of forces in x equals 0. That tells us that FA, or negative FA, times the cosine of 3 degrees plus FB times the cosine of 18 degrees equals 0. So we have one equation. There's 2 variables in there, FA and FB, and then there's some coefficients that I could evaluate if I wanted to. Summation of forces in Y says that FA times the sine of 3 degrees plus FB times the sine of 18 degrees equals, so on the other side of the equal sign, they have to add or balance this 30 pounds of the weight of the traffic light. And there's those two variables again, FA and FB, and I've kind of lined them up so that their coefficients, again, create my, here's a little 2 by 2 matrix over here, and here's the matrix that has the constants in it. So I can put those into a calculator. See, I had one over here, or no, right here, whoops, right here. So we still even have our calculator pulled up, we just need to put new coefficients in it. So let's see what those are. Oops, there we go. So this one needs to be negative, it's already negative, but negative cosine of 3. That one needs to be cosine of 18. That one needs to be 0. This one is sine of 3. That one is sine of 18. And that one is 30. And we get x, in our case, x corresponds to the variable we put first. So AFA, 79.6 pounds. So 79.6 and 83.5. Oops. If we did that right, then that would be the answer. I didn't check it beforehand, so I don't know. Those are reasonable-ish numbers. I do expect them to be high because they're not straight up and down. If one way to kind of think about it is if FA and FB were perfectly vertical, then they basically split the 30 pounds. So they would both be 15 pounds. And then the further they get from vertical, the more force they have to have in them because they're having to react the Y components are getting smaller and smaller, and that's the part reacting the 30 pounds. So I do expect them to have to be a good bit higher than the 30 pounds. So 80-ish pounds makes sense to me. I don't know. You'd want to check and make sure, but that seems at least a reasonable number. And we could have always typed something into our calculator wrong, but you should check it a couple of times just to be sure. But those at least seem reasonable numbers. As a little bit of an aside, not really directly related to free body diagrams, but related to drawing technical things. Here are a few, I guess I would call these drafting techniques, or drafting being the old term. I mean, it's still a current term, but it's done a different way. So now you go into SolidWorks and you do a little 2D drawing of whatever part you've made. And people use that, obviously, that's the current technology. What used to happen is a draftsman or a person who sat at a big desk with a giant sheet of paper hand drew all of these drawings. And so there were a set of kind of not guidelines. There were probably guidelines more than rules necessarily about how to make these drawings. And so I'll give you some of the biggest ones that will help you make your drawings, your free body diagram drawings or whatever it is you're drawing, a little better, or at least look a little more useful or more like engineering drawings that you might expect. So one of them is kind of picky and not that necessary to do, but it has to go. And I did draw arrowheads. So these arrowheads, there's actually a ratio for what an arrowhead should look like. Now it's more an arrowhead that's pointing to like a dimension or something like that, but the arrowhead itself should be 3, and not a unit here, but 3 whatevers by 1 whatever. So a ratio of 3 to 1 long to wide on your arrowheads. So if you get them roughly that ratio, you don't have to go like measure it of any of this stuff. And if you're doing SolidWorks, then they just spit them out that way, right? But if it gives you kind of a consistency, if you think about it, that you're not being confused if this is a little extra dot on your page or if it's the arrowhead on the end of a leader line or something like that, or on a dimension line. So that one's not super important, but it is actually something that if you were a drafts person back in the day, you would have learned that the ratio of arrowhead length to width is 3 to 1. Another one that is more important is, let's say that you have a body here. Actually, let's make our body a thicker line. So this is the body, and you're trying to dimension it. So there's a couple of things about this thing that you would want to do. So there's our 3 to 1 arrowheads. So a couple of things on here. One, the body lines are generally, so the lines that outline the figure, they're going to be thicker than dimension lines. So a drafts person, they would actually have multiple pencils, one that's got a thicker lead, one's got a really fine point on it, or things like that, where the body lines stood out, and the dimension lines, because they're drawing it in pencil, it's all the same color, or it ends up as a blueprint, it's all the same color. So you use weight of the lines to help differentiate the actual body from all these dimensions that might be on it. So the body lines are generally thicker than the dimension lines. I'm not saying go get a bunch of pencils and make them different or whatever, but that is something that helps. The dimension, so let's just put a number over here for it. Oops. Put a number. The dimension itself is not on the body. So this is something that you can't always avoid, but it's best if you can. So instead of putting this 4, right here, you put it off to the side. These little guys are called leader lines, and there's a gap between them and the body. So that the lines don't all run together. Not gap. So there's a little, and the gap is not super important on the size. I think there was like a certain size gap, as long as it's consistent and not too far, not too close. As long as they're roughly all the same. These roughly line up. You don't have one of these that's really long and one that's really short, unless you're putting multiple dimensions stacked together. We'll do that in a minute. What else did I write down? I wrote down some other things that I remembered. Oh, yeah, some symbols. So let's put a hole in this thing. Or some. Oh, wait, we were making them larger, weren't we? There. All right, so if we want to dimension this, then a couple of different ways you can dimension a hole, but normally you come over, and this one, the leader line does have to cross the body, and then you'll put some number. If that was 4, then this is like 1.5. We'll just do 1. And then this symbol means diameter. Capital R means that you're dimensioning the radius of the thing. So sometimes you want radius numbers, sometimes you want diameters. If this is a drawing that you're using to send to somebody who's going to make the thing, which one do you think they want? They want the diameter. You don't go measure the drill bit by its radius. So if you want a 1-inch hole, then tell them you want a 1-inch diameter so they can get a 1-inch boring tool of some kind, 1-inch drill or whatever they're going to use to make this 1-inch hole. Don't tell them it's a 1/2-inch radius. There are other levels to this also. If you actually were making a document to send to a machine shop, don't ever give them, you want 1. You need some amount of tolerance. Can it be bigger than 1? Can it be smaller than 1? To make it exactly 1 is extremely expensive. To make it 1 with some tolerance is kind of normal. So what do you really need? How close to 1 do you actually need? How close to 4 do you need this dimension over here? You need to have some tolerances on these numbers if they're going to be something that's sent to somebody to actually make, because once you tell them it is exactly 4, it gets into a ridiculously expensive process versus, oh, well, it can be 4, but it can be 4.05 or 3.95, and that's totally fine too, and that's a completely different operation. So that doesn't matter on drawing your free body diagrams. Obviously, on your free body diagrams, we're not going to be dealing with tolerances and things like that, not in this class anyway. But if you ever do need to draw something and send it to a shop, give them some room for tolerance. Let's see. Now let's go. I got my little isometric paper. Let's get into the 3D stuff. So here's some isometric paper. Grid. And there's different versions of this. Sometimes it's just a bunch of dots. I got this one from someplace. It says 123 RF on it, I guess. I don't know. But this one is actually got the grid lines on it, but some of them just have dots in these vertices everywhere to kind of give you the idea without putting a bunch of lines on the paper. There's a lot of different types. But the idea of my isometric grid, or if you're in SolidWorks and you drew a part and you do isometric projection or whatever, then ISO means something, right? ISO means equal. And then metric means something, means measure. And the isometric grid is set up so that you can draw things in kind of a 3D perspective, but they are going to have equal measure. So they won't look quite right. They don't have any perspective in them, so there's no vanishing point, but you can actually draw things and shapes that are, if you measure one length, like if I'm drawing a cube, a 3 by 3 by 3 cube, then I can actually go, let's make this a big one, probably to stand out. I can go 3 by 3, you know, and I actually can measure off units of 3 little line segments here, and I can, whoa, it's a little crazy. I don't know why it's picking up that. There we go. So 3 by 3 by 3 cube, and I actually can count 1, 2, 3, 1, 2, 3, 1, 2, 3, and they're all giving me an actual measurement. But it's not like I went and drew this thing in perspective where, you know, you have some vanishing point over here and you draw a cube. You know, it doesn't have, well, that's a really crooked line. You know, it doesn't have all of that perspective in it. So over here, you know, this is not the same length as that line. That line is not the same length as that line. But on the isometric one, they actually are all the same length. So it doesn't look quite right in your brain, but it measures. If you want to measure things, it's useful. So we're going to use this isometric paper. Let's get rid of that. To do things, particularly when we're having to give you a three-dimensional representation of some kind of scenario, 3D concurrent force system, and we want it to be readable on a 2D sheet of paper, we're going to use something like an isometric grid. So, for instance, let's make one of these types of cables right here, but in 3D. Not necessarily one of these, it's going to be at a different angle, but let's make it in 3D and show how it might work. So first we need a 3D coordinate system, so let's just put our origin right there. Is that going to be enough room? Actually, let's move it down some. Move it down to here. All right, so we'll put, really, we need to figure out how to turn that off. The y-axis over here, the x-axis over here, z-axis over here, that was y, and the origin right there in the middle. And what we want to do is we want to create some way that everyone looking at this could read the same information. If I just draw my force vector, if I just draw it, kind of out like this, then it's a little bit ambiguous to where that actually is. Is that in the XZ plane? Is that some vector laying down flat in the XY plane? Is it in some one of these planes at all? Is it just kind of out in space? So what we're going to do is we're going to go in and something like this. It won't always show up exactly like this, but here's one thing that'll show up like, let's go up. So that would be 4, 1, 2, 3, 4. Let's go in the X direction 3, 1, 2, 3. And let's go in the negative Y direction 2. Oops. 1, 2. So that's actually negative 2 because positive Y was going kind of to the right. And so now I have an endpoint here, and I assume I would have a beginning point here. And let's see if I can line this up and draw a straight line between them. Something like that. It would just stay still. Wow, not what I wanted to move. Oh, what's wrong with that? Why is it doing that? Maybe it doesn't like me to have the ruler there. Just do it by hand. All right, so there's the little rope kind of thing in 3 dimensions. So you're going to have to be able now in 3D concurrent force systems, a lot of times there's 3 of these ropes. So there's like dimensions everywhere. Another way this might be shown is the rope out there, and you just have the X, X is 3, Y is negative 2, Z is 4. You might just have the endpoints of that coordinate system or that endpoints of that line. And that would be a little simpler, like it'd be less cluttery, but that's what it means is those blue lines go, well, in this case, I guess you could go in order. You could go positive 3 in X, you could go negative 2 in Y, and you go positive 4 in Z, and you'd end up in the same spot. So if you want to go in that order, it doesn't matter what order you go in, but sometimes you'll get these pictures with these little lines like this, with the 3 and the 2, or negative 2 and the 4. Sometimes you'll get the endpoints of the coordinate, like the Cartesian coordinates, and they all mean the same thing. What we're going to do with this is kind of like when we went up here. We're right here, and we were doing these cosines of 18, cosines of 3 degrees. We're going to do that with this guy. So what we're going to do is first we need to know the length of this cable. So let's make it a little smaller to get some room, maybe over to the side. So the length of the cable. So we'll just call that L equals square root of, and then x squared, y squared, z squared. So that's the square root of x was 3 squared, y negative 2 squared, and z, that's a z, is 4. So let's see what that number is. 3 squared plus 2 squared plus 4 squared. 5.39. Let's just do 5.4 for making it a little easier. I'm not putting units on this thing, and that's another thing that I didn't mention with actual drafting things. Normally the units, like I wrote 4 and 1, normally the units are not on the picture. There's a little block, somewhere down at the bottom of the whole page that you've created that has your units in it and your scale and all that kind of stuff. In your figures, since you're drawing figures like this, you probably should put units on the pounds or whatever you might have. All right. Anyway, this is 5.4 length units, whatever units of length we're dealing with. Now, we're going to take each of our axes, x, y, and z, and we're going to create a cosine. So for x, we're going to do theta x is the angle between the x-axis and the cable, realizing that it may not be in any of my coordinate plane direction type things. It might, the cable is going kind of back to the left, so it's not in the xz plane, but I'm still going to measure theta x as if I created a plane between the x-axis and the cable. So I created this plane over here that's kind of tilted to the left a little bit, and I'm measuring theta x in that plane. That's the same thing as this, just there's only the xy plane. That's all we're doing. In 2D, you only have the xy plane. You don't have to deal with stuff that's out of that plane. In 3D, you may have to deal with stuff that's not in one of your xy, yz, or zx planes. And that's what we have here. So I'm going to say that theta x, or well, the cosine of theta x is equal to, the definition is adjacent over hypotenuse. So the adjacent side is going to be 3. That's the value of x in the x direction. The hypotenuse is the length of the cable, 5.4. So this actually is a number, 3 divided by 5.4. 3 divided by 5.4, whoops, 5.4 is 0.55 repeating. So 0.56. So that's useful. I'm going to do that for each one. So cosine of theta y, again, would be the adjacent side over the hypotenuse, but now I'm talking about, and it's going to be hard to draw this one, talking about that angle in a plane created by the y-axis and the cable, so it's kind of tilted out towards us. Not red. The adjacent side there is actually -2, and the hypotenuse again is the length of the cable, 5.4, so I get a negative number. 2 divided by 5.4, 0.37. And then I need one for cosine of theta z. So this one is, this guy. And this is where they start, if all of this stuff is labeled at once on one of these, and there's 3 of these cables, plus some kind of external force that's creating all the tension, then it gets really cluttery. So we tend to make them less cluttery, but that means you have to do more interpreting on where all these dimensions are talking about. So again, definition of a cosine is the adjacent side over the hypotenuse. For z, the adjacent side was 4. The hypotenuse was 5.4, the length of the cable. And then I get another number, 4 divided by 5.4, 0.74. So these are actually, anytime I need the cosine of theta whatever, I actually know it. I don't have to go figure out the angle. This is the same thing as when I had rise over run before yesterday. It's the same thing where I just know what the cosine of that angle is without knowing the angle itself. I could go figure out the angle if I wanted to, but I don't have a particular need to. So what I might do with that, let's see. For instance, you could imagine that I want to solve for a this is not a 3D concurrent force system. I only got one cable on it. I don't even show a force. We assume that, there's a force over here somewhere. But if well, let's make that force and let's call it F. Part of solving that, assuming I did have the other 2 cables and whatever external forces applied, then I would want to solve the equations. Summation of forces in the x direction equals 0, in the y direction, and in the z direction. So part of each one of those equations would be, I'd need to know the force components in x, the force components in y, and the force components in Z. So Fx for the one force that I have shown would equal F, the one that I drew up here in red, times cosine theta x, which I know cosine of theta x is 0.56. So F times 0.56. And Fy would equal that same magnitude F, but times the cosine of theta y, which would be F times, and it was a negative, 0.37. And then Z would be similar. F times cosine theta Z would be F times 0.74. And I'm starting to create the coefficients that are going to go into my 3x3 matrix that I can solve simultaneously. I just need the F, X, Y, and Z for cable number 2, wherever I draw it. I need the same thing for cable number 3, and I need all the constants, all of the, the weights or whatever it is that I'm lifting up. This assumes a couple of things. So when I drew the force F, I just drew one vector in the same direction as the cable. So this does assume that. So all of this thing assumes that the cable only supports an axial force. So there's no bending moment in it or anything like that. And that's for cables and ropes and chains, that's a reasonable thing to assume until, like, if it's a really big giant cable, then yeah, it's going to be pretty stiff. But most of the cables that you're going to deal with are relatively flexible compared to their axial strength. So basically what I'm saying is that if you have a cable, then it has a longitudinal axis and there's only that one axial force. So this thing, there's an axis and this force is along that axis. It could be either pulling on it, so like this, where it's in tension, or it could be pushing on it in compression. For cables, you really kind of assume they're in tension. So if this is true, this particular thing is an important concept. So if this is true, the cable only supports axial force, then the cable has a special name. The cable is a two-force member. One force, two force. So there's a two-force member. And that means a couple of things. It means that there are two equal and opposite collinear, although that kind of is implied by the other, but still I'll spell it out, collinear forces. So in here I've got two F's, same magnitude, but they're in the opposite directions. One's going left, one's going right. So it's always that way. There's two of the same magnitude and they're collinear, so they're on the same line, but they're pointing opposite directions of one another, wherever the line is oriented. And so normally, tension, so that's what I drew here is tension. There's forces pulling on the rope. So tension points away from the body, like I drew it here. And is usually positive in magnitude, so you use a positive number for it. When you're talking about the stress side of things, the positive here, I'm not talking about which way is it pointing, X, Y, Z, positive. Those are defined by your coordinate system. This is if I'm talking about does it create a positive strain or a negative strain or a positive stress or a negative stress, is that term. And compression would just be the opposite of this. So compression points toward the body and is usually negative in magnitude. All right. So a compression would just look different in that the arrows for F would be pointing inward towards the thing. And again, ropes don't really deal with compression too well. All right. Let's solve one. Somewhere over here I got one. Where'd I put it? Gotta find, there it is. Oh, go ahead. I don't know. Totally up to you if it's important or not. Oh man. Yeah. That's a different question though. Be direct. Don't give up. You get more stuff when you're direct and you don't give up. We'll zoom in on that once y'all copy that down. That's web work, my web work, so yours numbers are different. That's web work, homework 2, number 5, I think. Yeah, number 5. So yours will look like that picture, but it'll have different numbers on it. So this is kind of, there's a lot going on here. This one has a similar approach to what we did with this thing, except that it's given with these letters, A, B, C, D, E, F, G, H. Maybe there's no I. Normally I gets left out because it gets confused with a 1. J also may not be in there. K. Well, I and J get left out also because although K's in there, they can get confusing. Anyway, you should have some list of what goes into all those variables, and F for me is 1550 newtons. And then it's probably asking us, I didn't go actually copy down what it's asking, but it's probably asking us what is all the force in these. Now these are not cables, these little gray bars are struts, so they actually can support a compressive load. So they could have negative values for them because compression is negative, so they could have negative values in them. Whereas the ropes, you really don't expect ropes to have negative compressive forces in them. So here, this one's one of the harder ones in web work in that it, oh, turn the ruler off, there we go, in that it is a little bit misleading. So they've got an X, Y, Z coordinate system shown with the origin here, but that's not where all of your lines of action intersect. Right? That's just a convenient point to measure from. So in this particular one, I would actually go in and make the origin here. And then I went and for my numbers, I put in the X, Y, Z coordinates based on that new coordinate center because if you don't put the coordinate system origin at the point of intersection for all your concurrent force systems, then you start getting weird other things you have to deal with because your angles are measured from axes that aren't at your endpoints of your forces. And so that's kind of weird. You can make it work, but there's no sense to make it work. Just move the coordinate system over to a more convenient place. So I think for my numbers, I have gone in with these numbers down here and put the origin of my coordinate system at point A, and then figured out what the endpoints of each of these points B, C, and D would be in Cartesian coordinates. F, I haven't done the same thing with, but F has two components. It has a FZ component that would go straight down here, and it has an FX component that goes backwards in the negative X direction. I haven't gone and figured out what those things are yet, but that's Fx there, and there's Fz there. And so we'll need those when we write the X and Z equations of equilibrium. All right, so what we need to do is basically create all of this information for all three cables and the force. So we need the length of each strut, so not cable, but we need the length of each one of them, which is just doing the summation of squares, the square root of the summation of squares, and then figuring out all my cosines for every cable and for the force. I keep calling them cables, but they're actually struts. And then write these three equations, summation of forces in X, Y, and Z, all need to be 0. I'll need to sum to 0. And then put it into a solver where we can actually solve the thing. So let's zoom back in here. Let's start with just, we have AB, AC, and AD. Those are our struts. So let's do the length of AB is equal to the square root of, and then I've got my coordinates there, negative 12 squared plus negative 15 squared plus negative 4 squared. And these are all negative because of where I moved the coordinate system to, but that is totally okay. $19.6. Now, I am going to keep a reasonable set of decimals here. This is a web work problem though, so if I plug this into web work, chances are decently high that we won't get it right because I'm going to round off the numbers. If you're doing this for web work, then that 19.6, you probably need to keep more decimals. I'm not trying to get web work credit though, so. All right, AC would be negative 12 squared plus 0 squared plus 11 squared. $16.3. And then AD is negative 12 squared plus, oh wow, we'll do plus 10 plus negative 4 squared. All right. Oops. 16.1. The only real way you can check these is you have the endpoints 0, 0, 0 for point A, and then you have all of the points for B, C, and D. When you do the summation of the square root of the sum of the squares, then you know that what you get as a result should be larger than any individual number in the X, Y, or Z spot. So I have that, and they should be roughly on the same scale with those numbers, and I have that, so that looks like a reasonable, like those numbers, 19, 16, 16, seem like reasonable numbers. They're not out of the size of numbers I would expect. So that sounds good. Let's work on our cosines now. And if we write them, let's kind of do this in two steps. Remember, we're trying to get these forces, right? We want to write summation of forces in X equals 0. And I know that Fx, so the force, the X component of the force is that force's magnitude, which is what I want to know, times the cosine thing. So let's write it in a way that kind of looks useful for us to put into a matrix. So if we do it this way, let's see. Summation of forces in the x direction equals 0 equals. All right. So the force, this first row here, I'm trying to make basically a matrix here, a 3 by 3 matrix, and then a matrix here with the constants in it. So this one is going to be what would be in this first spot is the coefficient that goes with KR strut AB. We'll just do AB first. So this one will be all of my AB stuff. This one will be all of the AZ stuff. Oh no, AC. And this third column will be all the AD stuff. And these will be constants. And you can certainly take more steps to get to this point, like writing out all the cosines like we did with the rope, and then writing out your equations in kind of a generic term, and then putting the coefficients in, and you would end up here. So we're skipping several steps to get to this point a little more directly. Hopefully we don't make a bunch of mistakes in the process. All right, so what I want in here would be the coefficient that would go with the magnitude AB, so there's AB already kind of outside the matrix, and what coefficient would go with that to create the x component of AB. So it's going to be the cosine of theta x for strut AB. And so what we did there was we took the x value, which was -12, and we divided by the length of K-bar strut AB, which is 19.6. So that number, -12 over 19.6, is the cosine of theta x for strut AB, and I'm multiplying it by magnitude AB by putting it in this spot in the matrix. So the next one, if I put something in this spot, it should be the coefficient that goes with strut AC, or magnitude AC at the top there. So for that one, I would take AC, take its x component, which is also negative, they're all -12. So -12, but it has a different length, 16.3. And this number, -12 over 16.3, is the cosine of theta x for strut AC. And then AD would be the same thing, -12 over 16.1. So you can kind of see those numbers are right here and 19.6, -12 and 16.3, -12 and 16.1. And I've created this, oh, and the constants, the Fx is this little guy down here. I need to put it's not 0, there is a force component in that direction. So that force component is, well, I can do it this way. Since this force is in the XZ plane, I can actually figure out that angle. And why don't we do the process where we do, what was G? G is 7. So this is, let me draw this little triangle somewhere. So there, and there. So there's F. The height over here is 10. The base G is 7. So let's figure out what the length, it's actually a magnitude, but the length of F is 10 squared plus 7 squared is, no, I'd multiply them. 10 squared plus 7 squared, 12.2. So I can take here, the constant F is actually a known 1,550 newtons. So I might have to slide my deal over here a little bit because it's too close. Yep. That's the hypotenuse of this triangle. So this little triangle down here, that 12.2 is this. So I'm kind of doing similar triangles, basically. One triangle that's geometric, it's height of 10, base of 7, hypotenuse of 12.2, is similar to the triangle that has a 1,550 Newton hypotenuse, and I don't know its height and base. So I'm relating the geometry to the actual way the force breaks up into X and Y, or well, into X and Z components, not X and Y. So this one would be, I want the X, so 7 over 12.2. So what that does, that's actually a number, 1550 times 7 divided by 12.2. So the X component of the force is 889, and it's negative because it's pointing backwards in my negative X direction. So it's a negative number. So this top line, this line here is really this equation just broken out into a coefficient times a variable, coefficient times a variable, coefficient times a variable, and a constant. And normally you kind of put maybe your units over here, pound, force. So I'm really writing, oh, you know what? It is negative over here, but it would actually end up positive when I move it to the other side of the equal sign. So it will be a positive number in the matrix anyway, because I've moved it over to the other side. And then I'd write the same thing for y. And the only thing here is now, I don't really like to do this by just making patterns, but there's all the y's, and you have the same denominator here. So you would have negative 15 over 19.6, 0 over 16.3, and 10 over 16.1. There is no y component of my force because it's in the xz plane, so it doesn't go left or right at all. That might be a little hard to read from the diagram, but it doesn't give you any dimensions showing it deviating from in the y direction one way or the other, so you have to assume it's just in the xz plane. And then z is, it's the other set, is these guys. So negative 4, again, over 19.6, 11 over 16.3, and another negative 4 over 16.1. There is a value here. It's negative when I'm adding the equation, but when I move it to the other side of the equal sign, it'll be positive, and it would just be 10, or well, 1550 times 10 over that hypotenuse 12.2. So that's just a number I could calculate. All of these are just numbers that I could calculate. So the trick now is putting this into your equation solver. So I want to see if I can get them in over here. Let's see if I can find the solver. I never remember where it's at. There we go. All right. So this is one thing where you'll have one of these problems on exam 1, and sometimes there's one on exam 3. And really the only way they should be pretty straightforward, assuming you know how to make your calculator put in simultaneous equations. And you don't miss a negative sign somewhere. All right, so I have numbers, and I can't use my idea that normally they all need to be positive because some of these really should be negative. I could, and not everybody's good at this intuitively. Some people have to work at it. But I could try to visualize, all right, if I'm pulling down kind of backwards here, which one of these should be in tension, and which one should be in compression? So, you know, if you're hanging from this set of bars and you can visualize how they're arranged, then this one is going to be in tension because you're kind of pulling it apart. It's bolted up here and you're pulling down here, so you're kind of pulling on the edge. These two, they're tilted up a little bit. It's hard to see, but they're tilted up a little bit. And when I pull down on these two want to go into compression. So they need to have negative numbers. So if I get negative for AB and AD and positive for AC, then at least I've got the right pattern. And I got negative for the outside ones and positive for the inside ones. So what I got was, and most of your calculators are going to give you, here's what, well, let me just write down exactly what mine gives me. Mine said X, Y, Z, and because it doesn't know AB and AC and all that kind of stuff, and it shows a matrix that says negative 1090, 1058.4, and negative 1343, and it doesn't know units or anything. So that's what I got from my calculator. So how I figure out what it means is whatever set of variables I put in this column comes out in the top row of this answer matrix. So this is AB. What they have labeled as X is AB. And second one, I had AC in the second column. That'll come in the second row. So this is AC. And then the third column will be the third row in the answer matrix that they give me, AD. And the units will be whatever units I put on my constants, because the coefficients shouldn't have units. They're just a coefficient. The only units should be on the numbers in the constants matrix. So they're all in pound force. Now, the really scary part is if any of this works in WebWork, I won't be surprised if it doesn't, because we did do a good bit of rounding, so I won't be terribly upset if it. I want to get off there. I don't still have WebWork open. I don't know why it's. I don't know. Let's look. So it's homework 2, number 5. The question: find the force in each strut. So find those values. So we came up with, it's over here. 10, oh no, it's in my calculator. All right, so negative 1090. I don't even know what these units, actually these aren't pound force, this is all newtons. So, should be newtons. We should recognize my keyboard. 1058.4 newtons and 1343 newtons. And let's show the correct answers so that we see what we actually, hey, we got one of them right. But this is what happens in WebWork. Look, we put in 1058, it was 1056.5. That amount of rounding, this one's even closer. We put in 1043 and one at 1044.5. So there's a super tight tolerance in WebWork, and we have the right answers, and on an exam you'd be fine, but in WebWork it doesn't like that. So a better thing, we rounded right here is probably the worst set of our rounding. Those numbers right there. Because in here, in the matrix, I just put this in as an equation. So if I had put in 19.6 whatever, it'll probably spit out answers that were close enough for WebWork. I think there's like a 1% plus or minus that it'll allow you. Maybe sometimes it's less than that. So those are the right answers, but they're not the WebWork right answers. So you have to deal with that sometimes in WebWork. If you ever think you're stuck at that point, then that's when you click down here, email instructor down there at the bottom, and it'll send me what you put in, and it'll send me this thing. So I can say that, oh, well, they just rounded somewhere different, and I can tell you, I can basically cut that thing, paste it, send it to you, and here's what it really wants. You rounded wrong somewhere. if it gives me totally different numbers from what you have, then that's when it's useful if you put equations into the preview. This particular one probably wouldn't give me that much help having your equations in there, but I can at least tell you if it's web work or if it's you. Because there's no sense in sitting there for 30 minutes trying to track down the difference between 1056.5 and 1058.4. Because those are the same number for what we need, just not for what WebWork wants. All right, stop that thing. Wow. What I want. Don't know why it doesn't want to stop. I guess so. Are there questions? Yeah, go ahead. Oh, okay. I might can. I don't know if I can make this. So, I wish that would go off the screen though. All right, at least it's not on the screen. So I had these numbers. So these were embedded in WebWork, and you will have different sets. And what I did then was I went to the diagram, and for every variable, I wrote in the number that I had. So 10, 15, 15, whatever. And then, let's just take one of them. And I knew, just based on where X, Y, and Z are drawn, I know that that's the original origin. So basically, I went and subtracted 12 from all of the X numbers. So because I needed to move everything 12 units in the, or 12, I think these were centimeters in the X direction. And then I, let's see, subtracted 4 from all of the Y coordinates. You know, so like it gave me C was supposed to be 15 tall, but then I subtracted off these 4, so it made it 14 tall, and or 11 tall, which is showing up right there in the Z direction. And then for the Y direction, I didn't actually change anything because I just moved the coordinate system in the XZ plane, so all the Y values stayed the same. Here, the Y direction for point B is shown to be 15, which is in the negative Y, so it stays a negative 15. So it's only the X and the Z coordinates that changed, and basically all of the pins where the coordinate system started were at X equals 0. And since I moved, basically I made this point go, you know, along this path, which subtracted 12 from all of the X's. So I started at 0, subtract off 12, and then I moved it up 4. So I took whatever they had before. They didn't have these numbers listed at all. They were just given by the dimensions shown on the thing. But so I just subtracted 4 from all of the Y dimensions. These were at, like point B and point D were at Y equals 0, but when I moved the coordinate system up by 4 to get it up to where point A is, I had to subtract 4 from all of those zeros. So you could do it a couple of ways. I kind of just visually did it. What might be more pragmatic would be go in and put your original, all right, this point is X equals 0, Y equals 0, and Z equals 15. And then do the, all right, I'm going to subtract 12 from X. I'm going to subtract none from Y. And then I'm going to subtract 4 from Z. And that gives me my negative 12, 0, 11. So you could do it more like algebraically that way. If you list out the original point, figure out what you have to do to get from here to here, which means I have to move negative 12, negative 4. I guess maybe the tricky part is are those negative or positive? Is it negative 12 or is it positive 12? And it might be slightly more conventional to do it the opposite. You know, start here, then it's like, oh, I went down, so negative 4. Oh, I have to go back to get to here, negative 12. And that might make it make more sense. I just did it the other way because I moved from one point to the other and did it that way. But 15 minus 4. Oh. No, well, I moved the coordinate system 4 closer to it. So this is the Z, this is the Z direction. It was down here, and I moved it closer by 4, so I subtracted. So that's why I say it might make more sense to start at point A to figure out what you need to do, minus 4, minus 12, because then if you go to point A, it's like, oh, I have to go down 4, go back 12, and that might make the signs make more intuitive sense versus thinking of it as I started here and I got to point A, which might, it might seem backwards to some people. And a lot of these things, there's going to be several things that, not particularly yet, but this is one of the things where some people are going to look at it one way and some people are going to look at it the other way, and you just have to figure out which way makes more sense to you. Kind of the same with the angles. I didn't talk about it, but up here we have the 18-degree angle for FB. Some people may be way more comfortable with, oh no, that's not a 3-degree angle, that's a 177-degree angle. And what that does is then you don't have to worry about negative signs over here in your equation, because cosine of 177 is a negative number. So some people just like things more consistent, and some people like visualizing, oh, that's negative, that's positive. Just whichever makes more sense to you. There's not one of them that's right and the other one not. Anything else? All right, I'll see if I can make this thing stop recording. And I did post the video. WebWork wouldn't let me post it on WebWork, so I posted it on YouTube and linked it to WebWork. So